Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. In this module, we will learn different issues related to implementation of file systems. The learning objectives for this module are to understand the different layers in a layered file system, and for the implementation of the file system, a number of on-disk data structures and a number of in-memory data structures have to be used. So, we will learn what are the different data structures that help in the implementation of file systems, and we will understand how directories can be implemented. We all know that a file is a collection of related information, and file systems generally reside on secondary storage device, or they are kept in disks. And this file system will provide efficient and convenient access to the disk by allowing our data to be stored, located and retrieved easily from the disk. So, if there is no proper structure when you are placing information in the disk, then in that case, like it will be very difficult to know to retrieve data from the disk, to know where the data is kept in the disk and so on. So, rather than randomly placing information in the secondary storage device or in the disk, you structure in terms of files, and the files can be kept beneath directories, and you have a file system kind of a structure, a proper structure, and use that structure for easily retrieving and placing information in the disk. So, the file system is generally organized into many layers. We will see the different layers that are kept in a file system. You have the application programs written by the users, and the users application programs will use the logical file system, and the logical file system will invoke different data structures and modules in the file organization module, and the file organization module will use a basic file system, which in turn will use the IO control, which in turn will access the IO devices. Now, we will see each of these layers and the functionalities of each of these layers. So, first we will look at this IO control level, the IO control layer, which is placed just above the devices. So, what go into this IO control level? Those are the device drivers and interrupt handlers. So, device drivers actually act as an interface between devices and the operating system. They help to transfer the information between the disk or the device and the main memory. So, an example of input that is given to a device driver will look something like retrieve block number 123 from the disk. And when this instruction is given to the device driver from the upper layer, then the device driver will have to produce low level hardware specific instructions to the disk controller, and the disk controller will help or assist in reading and writing from the disk. So, basically here you have an instruction called retrieve block, which means you need to read the contents of block number 123, and the device driver will know how to translate this into hardware specific instructions, and it will provide instructions to the disk controller, which in turn will take care of reading from this block number 123. And the next level is the basic file system. This layer sits just above the IO control, and this will issue generic commands to the device driver to read and write physical blocks on the disk. This also manages memory buffers and caches. So, memory buffers and caches are maintained by the operating system in the main memory, and a block in the buffer can hold the contents of a disk block. So, you have a number of memory buffers that have been maintained, maybe it is called a buffer cache, and each buffer in this buffer cache can hold a block's data. So, whichever is read from the disk is copied onto these buffers in the buffer cache, and they can be used later if there is a hit again. And you also maintain cache, a cache which holds frequently used file systems metadata. It can even be the contents of a file, or it can even be information related to the file, like the owner of the file, size of the file, or the file control block, etc., and so on. So, metadata related to the file can be cached, and if the file is being used very frequently, then that information can be got from this cache itself. And now we have this file organization module. This is about this basic file system. This file organization module knows about the files and their logical and physical blocks. Logical blocks are with respect to a particular file. For each file, the logical block number will go from 0 to some n depending on the size of that particular file. But these logical block number, or if it is the first block in the file, that need not be mapped onto block number 1 in the disk, it can be kept anywhere in the disk. So, the physical block number will be different from the logical block number. So, the physical blocks need not match the logical block number. So, it is necessary to know where block number 1 of say file X is kept in the disk, or it is necessary to know the location of the file in the disk. So, for this, appropriate data structures and information is maintained by this file organization module to know the mapping between the logical block number of the file and the actual physical disk block number. The file organization module, it also has a free space manager which tracks unallocated blocks. So, in the disk you have a number of disk blocks, or the disk is divided into a number of disk blocks, and file contents are placed in the disk blocks in the disk, and some blocks will be allocated which holds the contents of the file, but there will be some blocks which are not allocated, which are free for use. So, the file organization module maintains information about which blocks are allocated and which blocks are free. So, if it knows the free blocks, then the next time a request comes to store the contents of a file, it will know these are the blocks that are free, and those blocks can be used for storing the contents of a file. And then above this layer you have this logical file system. This manages the metadata information about a file, or it will have all the details about the file except the contents of the file. The contents of the file will be kept in the disk, but all of the information of the file, like the size of the file, the owner of the file, permissions, access permissions of that file, it will know the locations of the disk blocks where the contents are kept. The actual contents will not be maintained, but the name of the disk blocks, the number of the disk blocks where the actual contents are kept will be maintained. Then it maintains the directory structure, that is in this particular directory which are all the files that are kept, that kind of a directory structure is maintained, and it will maintain information about the files which is called the file structure through a file control block, and this file control block will have all this metadata information. So, this file control block it is called an inode in Unix. It has got information about a file like the owner of the file, size of the file, the time when it was last accessed, when it was modified, the access permissions for the file, the location of the file's contents, and so on. So, we have seen that the file system is not maintained as a single layer, it is maintained as a multiple layers. So, because of this, the advantages are that the duplication of code is minimized, and the lower layers, the IO control and the basic file system code can be the same for different file systems, and above that the other layers above that can be modified for each different file system, or each file system can have its own logical file system and file organization modules. But the disadvantages of this layered file system is that it can introduce more operating system overhead, and because of that it can result in a decreased performance. And when the design of this layered file system is being done, it is necessary to decide how many layers you are going to use for the file system and what each layer should do, and each layer should have a different job. Both there should not be an overlap in the working in the different layers, and this becomes a challenge when a file system or a layered file system is designed. And so, there are many file systems in use today, like the Unix file system, the FAT32, NTFS, FAT32, NTFS are used in different flavors of Windows operating system, and there are different flavors that have been used in Linux operating systems. In different Linux flavors, different operating systems, different file systems are being used. ext3, ext4 are flavors that are used in the Linux file system, and Google has developed its own file system for its use, which is called the Google's file system. And now we will learn different issues related to the implementation of a file system. We saw that a file system can be layered, but now we will learn different data structures that are being used to assist the implementation of the file system. So, a number of structures are being kept on the disk as well as in the main memory for the proper operation of a file system. So, in the disk, structures are maintained which will have information about how to boot an operating system that is stored in the disk, and the total number of disk blocks that are present in the disk, and of these total number of disk blocks, how many are free disk blocks, and which is the location of the disk blocks which are free, and what is the structure of a directory, what are the contents of each directory, and individual files. So, information about individual files, say the inode in the case of Unix, all these are maintained in the disk. And you also have a number of in memory structures, and these structures are maintained in the main memory, and these are helpful for file system management, for caching and so on. So, now we will see each of these on disk data structures. First is a boot control block. This boot control block is usually the first block that is kept in the disk. Say if a volume of the disk or a partition of the disk has an operating system or stores an operating system, then information about how to load the operating system into the main memory is maintained in this boot control block. We all know that an operating system has to be loaded into the main memory while the system works. So, at the time of boot up, the bootstrap loader will try to find out this sector 0 or the first block present in that partition, and the partition will have information needed to boot the operating system. Suppose if that partition does not have an operating system, then this block will be empty, the boot control block or the first block will be empty. In Unix, this boot control block is called a boot block. In NTFS operating system, it is called a partition boot sector. So, this is one structure that is being maintained to help in booting an operating system. And then we have the next data structure called a volume control block. This has information about a particular volume or a partition. What kind of information? That partition will have many number of blocks. So, the total number of blocks that are kept in that partition, then what is the size of each of those blocks, and if there are free blocks, the number of free blocks that are maintained in that partition, and it will also have pointers to the free blocks, or it will have the addresses of the free disk blocks. All these will be maintained in something called a volume control block. In the case of Unix, following that boot block, you will have a disk block which maintains this information which is called the super block. In the case of NTFS, this is stored in the master file table. Now, the next structure is the directory structure. This directory structure is for each file system. So, as we all know, the directory structure is used to organize files. You will have directories, subdirectories beneath it, files beneath it and so on. And what is maintained in each of the directories? The name of the file is maintained, and also the associated information will be kept. In the case of Unix, you see that the names of the files and the inode numbers of those files will be kept in each directory entry. In NTFS, this is stored in a master file table. And then one more structure we have got, which is called the per file control block. So, for each and every file, metadata about that file should be maintained in some place. It is maintained in a file control block. As I told you, in the case of Unix, it is maintained in an inode. So, what metadata will be kept in these files? It will have all details about the files, like the owner of the file, the size of the file, etc. and so on. And then it has a unique identifier number to allow the association with a directory entry. For inode there is an inode number. Okay. In NTFS this per file control block is stored in the master file table. Now, we will see different in-memory structures that are maintained for the implementation of the file system, that is structures that are maintained within the main memory for the implementation. One is a mount table. We have learnt about this mount table in an earlier module. That is, when you want to logically attach one file system to another file system, then information about this mounted volume is maintained in this mount table. The mount table have information about the directory onto which the new file system is logically attached to, and the device file name of the mounted file system. All these will be maintained in a mount table. The second structure is a directory structure cache. This directory structure cache, it holds the directory information of recently accessed directories. So, if you want to access the same directory contents again, then you do not have to read from the disk and then access the contents. You can just make use of this cache, look into the cache and get the information about the directory, maybe the contents of the directory from the cache itself. And then we have something called the system wide open file table. This is a common file table that is being maintained for all the processes that are present in the system, and the entry of this open file table will have information about the FCB of each file. Or what is the FCB? It is the file control block. In the case of Unix, it is the inode, or it will have the metadata of the file. So, that is kept in this system wide open file table. And then we have something called the per process open file table. The system wide open file table has got entries for all the processes that are present in the system, but in the case of this per process open file table, you have a file table, open file table for each and every process. So, this will have information about the files that are opened by that particular process, and the entry here will point to the appropriate entry in the system wide open file table. And then we have buffers. So, these are buffers that are kept in the memory to hold the contents of disk blocks. So, disk blocks have the contents of files, and when you are reading a file from the disk, you store the contents of the file in this buffer that are kept in the main memory. So, the next time if you want to access the same file's contents, you can read it from these buffer rather than reading it from the disk the second time. So, even if you are writing to a particular disk which is a part of a file, you can write to these buffers and the writing can be delayed for some amount of time. So, you maybe can read from a particular block, you can write into the block, again read, write, etc. and so on. So, changes, a number of changes can be done to a particular block of a particular file, but you do not have to write it each and every time to the disk. You can maintain it in the main memory in this buffer, and after all updation have been done, then you can write it back to the disk. So, now we will see how these structures are being used when a new file is created. So, we saw that the topmost layer in the layered file system is the application program. The application program will call a logical file system. The logical file system will know that name of the directory structures. Here we need to create a new file. So, the application will say that a file with name say ABC has to be created. So, now the logical file system will know the directory structures. So, it should know the parent directory where this particular file has to be created, or it will be created in the current directory. And the logical file system will allocate a new file control block, because a new file has to be created, a new FCB will be assigned for this file. In the case of Unix, the FCB is nothing but an inode. So, an inode will be assigned or will be allocated for this new file that has been created, and then the system will read the appropriate directory into the memory. Say if you are trying to create this file in the current directory, then the current directory's contents will be read into the main memory. Now, what we need to do in the directory, you need to create an entry for this new file, and the data related to that FCB has to be written in that particular directory's entry. So, you know the directory. So, you have read the directory from the disk into the main memory. Now, in this directory's contents, you need to write the name of the file and the FCB, and once this entry is being made, this directory can be written back to the disk. So, a typical file control block will look something like this. You will have file permissions, file dates, when it was created, when it was accessed, when it was written, etc., and so on. The owner of the file, the group, the access control list, the file size, the data blocks, and so on. All these will be kept in this FCB. So, now we will see what happens when an existing file is to be opened. So, the open call given by the application will pass a file name to the logical file system, the name of the file which has to be opened. This call will first search the system wide open file table to see if that file is already in use by another process. It may be possible that the file is opened by another process at the same time. So, looking into the system wide open file table, it will find out if there is an entry for that process, for that file by some other process. So, if there is an entry, then it means that the file has been opened by another process. So, the same entry in the system wide open file table will be used by this process also. So, it will create a per process open file table entry for this file, because this is a different process that is opening that file. So, for this process there will be a per process open file table. In that an entry will be created, and from that entry a pointer will be made to point to that system wide open file table entry which is already existing. If the file is not already open, then you need to search in the directory for the given file's name, and it is possible that part of the directory structure can be cached and kept in memory, as I told you earlier. So, if it is present in the cache, then you can read it from there, or you need to read from the disk. So, once the file is found in the directory's content, so you read the directory and search into the directory to find the contents of that file. There will be an entry in the directory for this particular file, and the FCB is also kept, the information about the FCB is also kept in the directory's entry. So, now you get information about the FCB, and the FCB is now copied into a new entry in the system wide open file table, because the system wide open file table in this case does not have an already existing entry. You are creating an entry for the first time. So, you need to get hold of the FCB of the file from the directory and make an entry in this system wide open file table and copy the FCB into the system wide open file table. So, the FTB entry will also have information about the number of processes that have opened the file, that is in that file table entry you will have the count of the number of processes that have opened the file. And now an entry is made in the per process open file table. This entry is made to point to the system wide open file table. So, the entry will also have information about where the next read write should be done on the file, the access mode in which the file is open, and so on. So, the system wide open file table entry has information about the number of processes that are using that particular entry and the offset within the file where the next read or write should happen, and the access mode in which the file is open, say whether the file is open for in read only mode or write only mode or read write mode, and so on. All those information will be kept in this file table entry. And finally, what is returned is the open will return a pointer to the entry in the per process file system table. So, after this all file operations that have been done, after the open you will have to read from the file, you may have to write into the file, and so on. So, all file operations that have been done will use this pointer to access the per process file system table, and thereby it can make use of the system wide file table entry which will have the FCB. FCB will have information about the location of the contents of the file in the disk. In Unix, this pointer that has been returned is called a file descriptor, and in the case of Windows this is called a file handle. Now, we will see what happens when a file is closed, how the structures are being used. When a process is closing a file, the per process open file tables entry has to be removed, because the file is no more going to be used by the process, but there is a pointer from here to the system wide open file table. So, you use that pointer to the system wide open file table and access that entry and try to find out the number of processes that are using that particular file. So, that count is decremented. If the count becomes 0, then it means that no process is using that file as of now, only this was the only process that was using, and hence the updated metadata is copied to the directory structure in the disk. So, you had something called an FCB that is maintained in this entry which has got information or metadata about that file. All this information are copied onto the disk. The system wide open file table entry can be removed now because the count here is 0, no other process is using this file as of now. So, here you can look at this diagram, you can see that the user is providing open of a file name, which means that it needs to access the structure of a directory, and the structure of the directory can be kept in the disk, is actually kept in the disk. So, from there you can copy it into the kernel's memory, and from there you can access the file control block. And then say if you want to read from a file, so you need to read provide the index. This index is actually a return of this open call. So, that index is used to access the per process open file table entry. From there you follow the pointer to the system wide open file table entry, and then from there you can access the FCB, and the FCB will have details about the address of the disk blocks which contain the data in the disk. So, now having seen this in memory structures, we will look at how directories can be implemented. So, the simplest way to implement a directory is to have a linear list of file names, and that can have pointers to the data blocks where the contents of the file are kept in the disk. But this is very simple to program, but the problem is it is very time consuming to execute. That is, to create a new file, you need to search the directory if another file is present with the same name. If there is no such file with the same name, then a new entry has to be added to the end of the directory. And to delete a file, you need to search the directory for that file and release the space that is allocated to that file. But now, when you delete this entry, you have to reuse this deleted entry. How do you reuse the deleted entry? You can mark that the entry is unused by assigning it a special name, or you can attach it to a list of free directory entries, or what you can do is that you can copy the last entry that is kept in the directory to this free location and decrease the length of the directory. Or another way is to maintain the entries as a linked list, so that deletion will become easier and it will reduce the time required for deletion as well. But the disadvantage of having a linear list is that finding a file requires linear search, that is, you need to search one after the other to search for a particular file, which will make the access very slow. And operating systems implement software cache to store the most recently used directory information, which can make the search easier. And you can also maintain a sorted list and then allow a binary search within that list, which can reduce the time, but maintaining the sorted list again becomes difficult. Whenever you are adding a new entry, then you need to ensure that the list is maintained as a sorted list. So, rather than having a linear list, you can go for a hash data structure. So, you can have a linear list to store the directory entries, but you can have a hash data structure also. This hash data structure will help in pointing to the entries or getting the entries in a much easier way. The hash table will take a value computed from the file name and it will return a pointer to the file name in this linear list. Because of this, the search time is reduced. But the problem is that you need to provide provisions for collisions, that is, if two file names they hash to the same location, then what to do. So, you can have a linear list or a hash data structure for implementing directories. So, the summary of what we have learnt in this module is that we learnt what a layered file system is, what are the different layers that go to the file system, what are the functionalities of the different layers. Then we understood that a number of on-disk structures are maintained to the implementation of this file system, and a number of in-memory structures are also maintained for the implementation of the file systems. We saw the functionalities of the different structures, and then we saw the different ways in which directory can be implemented. References. Thank you.